Warm greetings, friends, and my dear students. Today I am going to deliver a lecture video on thin cylindrical shells. Thin cylindrical shells, already we have seen it. So we are going to see about the thin spherical shells. We have defined the thin cylindrical and the thin spherical shell in the previous videos. Anyway, I am going to define the thin cylindrical shell as when the thickness of the shell is less than or equal to 1 by 15 to 1 by 20th of the diameter of the spherical shell. So in the case of thin spherical shell, there will be no shear stress at all in any wave section of the spherical shells, because if you are able to find the maximum shear stress, tau max or q max, so that is equal to 0, because tau max is equal to the summation of algebraic summation of the principal stresses divided by 2. So that is equal to sigma 1 minus sigma 2 by 2. So here sigma 1 is equal to sigma 2, that is equal to P into D divided by 4T, where P is the pressure inside the spherical shells and D is the diameter of the spherical shells. When the thickness is small for a spherical shells, it holds a lot of pressures compared to the thin cylindrical shells. So therefore, the tau max or q max is equal to PD by 40 minus PD by 40 whole divided by 2. That means it is equal to 0. So I am considering the thin spherical shell as shown in the diagram, where D is the diameter of the spherical shell and T is the thickness of the spherical shell, and I am using sigma 1 sigma 2, that is the hoop stress and longitudinal stress. So both are equal, so that is equal to PD by 4T. Already I have told you P is the pressure inside the spherical shells and D is the diameter of the spherical shell and T is the thickness of the spherical shell. So you know that the basic fundamental equation for the volumetric strain epsilon V or small ev is equal to the ratio of change in volume by original volume. So therefore epsilon V is equal to delta V by V. So delta V is equal to volumetric strain into original volume. Volumetric strain will be of epsilon V, that is equal to 3 times the strain of the diameter. So that is equal to 3 into delta D by D. Already I have written in the case of the diagram. And if you are able to find the volumetric strain, so this volumetric strain will have a value which will be less than the cylindrical shell, because wherever you take the section of the spherical shell, it will be of circular in section. So that's why the volumetric strain is 3 times delta D by D. So if you are finding the changes in the dimension, that is the diameter of the spherical shell, so epsilon V into the original volume, epsilon V 3 into delta D by D into volume is pi by 2 into D cube. So from this you can able to find the changes in the diameter of the spherical shell. So here Because of spherical shell in nature, that is a sphere, the length will be of a diameter. Wherever you cut the section of the spherical shell, it likes a circular in section. And if you are able to find the Q max, already I have told you 1 by 2 into sigma 1 minus sigma 2, where sigma 1, sigma 2 are the major and minor principal stresses. So because sigma 1 is equal to sigma 2, the numerator will be 0 divided by 40 means into 1 by 2, so automatically it will become 0. So that's why the cylindrical shell are more economical than the cylindrical shell, because of the reason there is no shear stress at anywhere section of the spherical shells. So in this case of spherical shell, if the fluid pressure and the diameter is given, you can able to find the circumferential as well as the longitudinal stress. Here the circumferential stress is equal to the longitudinal stress. So that's why F1 is equal to F2, that is equal to PD by 4T. And from this condition, you can design the thickness of the spherical shell also. You know that the maximum stress is hoop stress, that is equal to PD by 4T. So the thickness should be less than or equal to, greater than or equal to PD by 4F, where F is the working stress or the allowable stress in the material of the spherical body. So from this, you can able to design the diameter and the thickness of the spherical shell, or the diameter is given, you can go for the design of thickness, and the fluid pressure is given, you can able to find the F1 and F2, that is the circumferential and longitudinal stresses. And also you can able to calculate the maximum shear stress, and from this we can give the diameter of the spherical shell and also the varying dimension of the diameter of the spherical shell. Here the dimension is only the diameter. So that's why the spherical shell is more economical than the cylindrical shell. Thank you very much for patient listening. வாழ்க வையகம், வாழ்க வளமுடன். Goodbye.